We have now completed the new set of rows for the third simplex tableau. For the PJ column, third row, the value now is 10, which comes from the value of x2, which was the entering variable. The new values of PJ minus CJ row can now be easily computed. Since there's only one positive entry in PJ minus CJ row, S1 column now will be the optimum column. And we now find again the pivot row. We divide quantity column with the optimum column. For row 1, we have negative 15, so we disregard it. Row 2, 48 and 1/3. Row 3, we disregard. And row 4, disregard. So, since there's only one valid value out of the 4 rows, we assign row 2 as the pivot row. Then we compute for the new pivot row values. Pivot row divided by the pivot element generates the following values. Then we compute for the values of new row 1, new row 3, and new row 4. Then we have the new set of rows for the fourth simplex tableau. With the new entries, we compute for the values for the ZJ row, and then the values for the PJ minus CJ row. Since there's only one positive entry in the PJ minus CJ row, we set the column where it belongs as the optimum column, that is, the x3 column, and x3 now is the new entering variable. We find now again the pivot row by dividing the quantity column with the optimum column. For the first row, we disregard the value since 25 divided by 0. Second row, we have a negative quotient, so disregard. Third row, disregard. And fourth row, we have a positive quotient. So we set row 3 as the pivot row. Compute for the new pivot row. For the new row 1 values, new row 2, and then new row 3. We completed the new set of rows for fifth simplex tableau. After entering the values for the fifth simplex tableau, we now compute for the values of the CJ row. Okay, and the values of the PJ minus ZJ row. Notice that the three non-zero values in the PJ minus ZJ row are all negative. That means we have obtained the optimum table, and we can now make a decision. x1 equals 25 units, x2 equals 13 and 1/3 units, and x3 equals 8 and 1/3 units, where maximum P equals 425. This next example is a minimization problem. The objective function has two basic variables, two slack variables, and two artificial variables, subject to the given constraints. After conversion, we now obtain the new program of constraints. Then we construct the initial simplex tableau and fill in the entries which are the coefficients and constants from the new program of constraints. The entries in ZJ row are determined next by taking the sum of the products of CJ column entries and every variable column entries. After that, we can easily calculate for the values of CJ minus ZJ row. By looking for the lowest valued entry in the ZJ minus ZJ row, we can determine the optimum column. In this case, that is negative 58 in the x2 column. Finding the pivot row is easy, and that row is row 3, which has the least possible quotient. New rows values are computed as follows. Take note that the multipliers to the new pivot row are the negative values of the optimum column. With the new rows, we construct the second simplex tableau. Compute for zj row values as well as cj minus zj values. Then the new optimum column is the x1 column, and the new pivot row is row 1. Find the values of new rows. Okay, and after that, construct the third simplex tableau. We then compute for zj row values, then cj minus zj row values. As the table shows, the non-zero entries in zj minus cj row are all positive. That informs us that the optimum table has been obtained. Decision: x1 equals 5 and 5 over 9 units, x2 equals 8 and 8 over 9 units, and minimum of c equals 62.22. That wraps up this short video presentation. Thank you.